Hello again from Berkshire Guitar Amplifier Repairs in Reading, England. Stuart Smith at the bench as ever, and today we have a Marshall JTM100. Very nice amp, of course, lovely. The sort of thing I really enjoy working on. Bit of a mystery on this one. He bought it second hand on spec and it had a bad hum, and he took it apart apparently, and there was a power resistor inside which had burnt out or got very hot, so he replaced that, and he replaced the valves I think, and also the filter caps, but still got some sort of a problem with that power resistor getting too hot. I'm not quite sure what that resistor will be. I can't recall the circuit for this off the top of my head, but I think I'm not going to do anything technical apart from take the chassis out, and let's have a look inside and see if we can see anything that looks cooked. Whoa, look inside this. I don't think I've seen one like this before. Beautiful tag board construction, quite original. All these caps are original, and I'd like to change those, but I can't see anything that's getting hot. I wonder where something that's getting hot could be. If only there was a sort of clue as to what was getting hot. Aha, I think there's a little... Could be wrong. Check me out here. Is there a little clue here? Ooh, look. I think it might be this resistor that was getting hot. It's just my years of experience, really, that tell me that that's probably the problem area. Okay, well, he's very thoughtfully put a label on. Joking aside, that doesn't look like it's been getting hot to me. It's the print on it's perfectly okay. No idea what it does at this stage. No point in even guessing. I think I'm going to need to pull the schematic for this. 8K2 at, I don't know what, 5 watts or something. Anyway, carrying on along here, they don't look like they've been replaced, but they look newer. These are ancient. Look at these. Golly, these are probably the original caps. And 33 microfarad 450 volts DC, so these are the HT caps. You'll notice I'm not touching them, by the way, I'm just touching the bodies. Right, so they're the HT caps, and looks all quite nice, really. I think what I'm going to do is grab the schematic for this and just see what this resistor is doing. Then I think my next idea would be to bring this up slowly on the variac with a couple of bias meters on the couple of the power valves, just so that we can see what's going on, and then take it from there, really. I can't imagine there's too much wrong with this. So let's do that. Right, I've been doing a little bit of research on this amp. It's a JTM100 Super PA, and the schematic of this is very rare. I've been unable to track it down, which is quite unusual, but I can't find it. And on several sites it lists this diagram as the one that's missing. Not this diagram, the one for the amplifier we're working on. However, it's based on a JTM 45, and I've seen a schematic for another JTM100 too, and they all use the same idea. So let me just talk you through this. We have, this is the resistor that's getting hot. It's 8K2 2 watt. And the customer said in the original amplifier, I think he said this is burned out, and he's put a new one in, and it's still getting way too hot. Okay, what does it do? Well, it takes the HT here and feeds the screen resistors. Now we have 4 valves in our 4 power valves in our amplifier because it's 100 watt. So basically we have another 2 valves and another 2 screen resistors, and the screen resistors in our amp are 1K, not 470 ohms, but basically it's the same idea. So this is our screen resistor setup. If this resistor is getting too hot, one of these valves is pulling too much screen current, and that would cause this to get very hot. So here is the setup. I've just sketched it out for you. on the amplifier we have the screen HT, we have our 8K2 resistor, which is the one that's getting hot, and we have these 1K 5 watt actually resistors feeding pin 4 of each of the power valves. Pin 4 is the screen, so 1, 2, 3, 4 power valves, 4 pin 4s, and 4 1K screen resistors. So one thing to notice immediately is that all the screen current goes down through this resistor. It gets split off, of course, down the 4 resistors, but all of it goes through here. And this is a much bigger value resistor than this, so it wouldn't take much screen current going down there to cause this to overheat significantly. Now, before we get into a little bit of Ohm's law, which I want to do with you to see what's going on here, let's just have a look at that in actual practice on the amp. Let's get rid of this label. So let me point out what we're looking at physically here. Here are our 4 power valves, 1, 2, 3, 4. Here are our 4 screen resistors at 5 watts, 1K, 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 1K. And here is the 8K2, ostensibly at 2 watts, but this is a replacement, and I think that must be at least 5 watts there. This is the one that's getting very hot. Now, it's interesting this. Someone may be able to tell me what's going on here. Why are the screen resistors here 5 watts? Because they're not taking much current. If these were indeed drawing, consuming 5 watts of power each, they wouldn't, of course. That's very hot. That's very hot. This would be consuming or dissipating a lot more power than that, well in excess of what this resistor would be able to cope with. If there were just one of these resistors here, not 4, and it was dissipating 1 watt, then because this resistor is 10 times bigger roughly than this would be 10 watts immediately. In other words, well in excess of its 2 or 5 watts. And if each of these was consuming a watt, this would be 40 watts. It would burn out immediately. So how come these are so high rated compared with this one here? I expect to see the opposite. I expect to see these 1 watt and this maybe a 10 watt. But anyway, we won't worry too much about that. Someone may have the answer, I don't. We now need to spend just 5 minutes going through a little bit of theory. You don't need a lot of theory to repair guitar amps, but you do need Ohm's law, and you do need to know about power in resistors and things. So I'm going to talk you through that in connection with this problem here, and that may help you to understand. I've done a very good video on Ohm's law, kind of Idiot's Guide to Ohm's Law, so if you haven't seen that and you don't know Ohm's Law very well, I suggest you go and look at that. If you know Ohm's Law inside out, back to front, you can calculate the power in resistors inside out, back to front. Skip forward maybe 5 minutes or so, but I'll just talk the other people through what we're doing here. Right, before we do too much more, I'm going to level with you and say that I've never really totally understood what the screen does in a valve, and I thought, come on, you know, about time you learned. And I went online. I spent a couple of hours looking online. Bottom line is, it's not very easy, which is why, of course, I don't immediately understand it. But anyway, for your interest and nothing more, the screen is another electrode that's put between the control grid and the plate. And inserting this extra electrode, they found out that it helped in certain various ways, and this is rocket science, so don't worry too much. Apparently it does these things. That's particularly important. It reduces the capacitance between the control grid and the plate, increases the tube efficiency, reduces distortion, increases gain. I have no idea how any of that works. I've got a degree in electronics. I'm only saying that just to let you know that I'm not a layperson in these matters, but I have no idea how this works, and neither is anybody else as far as I can make out. Do feel free to do your own research on the internet, but I bet you'll find the same thing I did, which is not a very simple explanation of what the grid does. Anyway, suffice it to say that sum of the tube current. Here's the cathode, here's the anode, here's the control grid. This is where you put your little signal, and this is the grid that affects the attraction of the electrons from the cathode here up to the plate, and the current flows up here, depending on your current conventions. So the screen sits in here and does its magic on pin 4. Let's not worry about the magic that it does. But the upshot is that some of this plate current ends up going out the grid, or out the screen, or in the screen, depending on your conventions. And here is our typically 1K screen resistor, and this goes up to a very high voltage like HT. Right, now how much current does go through here compared to going through here? And the rule of thumb is 5%. So 5% of the cathode to anode current ends up going through the grid. Let's take a look now then at the theory section, which will only last about 5 minutes. And I just want to show you something here. A typical tube will take, let's say, 40 milliamps current through it. You would bias it typically at about 40 milliamps, what I call tick over rate. And that means that typically 5% of this will be going through the screen. Well, 10% of that is 4 milliamps, 5% is 2 milliamps, so 2 milliamps will go through the screen. Let's now see how much power our our screen resistor will take. Well, we know it's a 1K resistor, and we know it's got 2 milliamps going through it. The formula for power on a resistor is the power through the resistor is I squared R. So it's the current squared times the resistance. Okay, well, let's do some sums then and see what kind of power dissipation we might expect from in this 1K resistor. So it's a 1K, 2 milliamps through it, the power is I squared R. Let's just plug some numbers in. It's 2 milliamps, so it's 2 times 10 to the minus 3 squared times 1K, which is 1,000 ohms, so it's 1,000 ohms. Let's do the sums here. 2 2s are 4. 10 to the minus 3 times 10 to the minus 3 is 10 to the minus 6 times 1,000, or 10 to the 3. So we have 4 times 10 to the minus 3 watts being consumed by that resistor. I make that 4 milliwatts. I hope I'm not wrong on my numbers here. In other words, under normal conditions, we're talking about 4 milliwatts being consumed by this screen resistor, but it's rated at 5 watts. In other words, 1,000 times that current. Now, because the current goes up with I squared, things can get out of hand pretty quickly. So I don't know. Let's say something crazy happened and 20 milliamps flowed through the screen under certain conditions. Well, now we've got P equals 20 times 10 to the minus 3 squared times 1,000, and that's 400 times 10 to the minus 6 times 10 to the 3. That's 400 milliwatts, or half a watt, roughly. So suddenly we've gone from nothing, like down in the noise here, to half a watt. Suddenly in the resistors, you put your finger on it, you think, oh, actually, that's warm, it's getting warm. And of course, if we went up to, just up to 30 milliamps, suddenly, well, we've got 900. We've got 1 watt. This will become 900, and suddenly we're into 1,000 milliwatts or 1 watt, and suddenly, oh, that screen resistor is getting hot. So, but under normal conditions, nothing terribly much happens to this screen resistor, and I'm confused about why. I've never thought about it before. I'm just confused about why it's such a high wattage. They're 5 watts, these resistors. Okay, well, let's just see what happens to this one if we have a typical level
of like 5% of our cathode current going through the screen. So we said a couple of milliamps, didn't we? Let's make it a little bit more generous. Let's make it 3 milliamps. Let's have 3 milliamps going down through each of these resistors. Well, we've got 3, 6, 9, 12 milliamps. So there's 12 milliamps going through our 8K2. Let's do a little bit of Ohm's law on that. So power, if you remember, is I squared R. So the power that will be dissipated in our 8K2 resistor under normal conditions, remember, is 12 milliamps squared. Well, we don't need to do this. 12 times 12 is 144, call it 150, times 10 to the minus 6 times 10 to the 3, so 150 milliwatts. Again, nothing. That would be stone cold, that resistor. You wouldn't even feel 0.15 of a watt going through there. So again, under normal situations, with 3 milliamps going through here, everything's fine. If for some reason these went up to 10 milliamps, well, suddenly we've got 40 milliamps going through here, through this one. See, because this is a much bigger resistor, everything becomes much more serious. It's taking all the currents of the screens, all 4 of them, and it's 10 times the size of the screens, roughly 8 times the size. Therefore, it's going to start to increase its power. So 10, 20, 30, 40 milliamps, 40 milliamps down there. Now we're into I squared, 40 times 40 times 40 times 10 to the minus 3, so it's times 10 to the minus 6. So 400, 1600, and then times our 1K resistor, so it's 1600 times 10 to the minus 3, 1, 2, 3, it's 1.6 watts suddenly. From 150 milliwatts, now we're 1.6 watts on a ostensibly 2 watt resistor. You put your finger on that, you go, oh, ouch, that's getting hot now. So my point here is, first of all, I hope it's interesting for you to go through Ohm's law regarding power, but you don't need much of an increase in current down one of these before you're really in trouble with this resistor here, and it will start to get hot. Right, so that's the end of the theory. There we go. Right, so now, okay, what's the game plan? I haven't even turned this amp on yet. The game plan is to turn the amp on at a lowish voltage. I don't know, I'm going to get, instead of, these have insanely high plate voltages, these JTM100s, 550 volts or something like that. We're going to turn the amp on and get like 300 volts DC instead of 500. 300 volts on the HT instead of 500. And I'm going to see if anything's getting really hot first of all. I'll wind it up slowly on the variac. Look out for things getting really toasty. I suspect they won't do it at a lowish plate voltage. Now, of course, what we can then do, once we've got this thing steady state and not cooking, we can measure across each of these 1K resistors with a voltmeter, and we can apply Ohm's law, and I can tell how much screen current each valve is taking individually. And if we go 3 milliamps, 3 milliamps, 3 milliamps, 38 milliamps or something, we're going to know we've got a problem maybe with one of these valves drawing too much screen current. So the only reason I can think of for that resistor to get too hot and even burn out is if one or more of these valves is drawing too much screen current. A lot of waffle from me, sorry about that, bit theoretical this one, but let's turn it on, bring up the voltage on the variac and see what kind of volts drop we're getting across some of these resistors, and that'll tell us the currents that are going on inside. Okay, here's the setup. I've got the amp plugged into the variac, which is just off screen there, and I can wind up the voltage, and I've got my meter here checking the voltage across this 8K2 resistor. I'm going to wind up the variac to about 100 volts AC. Let's do that. Now there we are. Ooh. It's interesting. Did that suddenly pull a load of current? Okay, I can hear a very slight sort of clicking sound when I go up above a certain voltage, which is not very much volts. I'm bringing it up now. Why is this on negative voltage? That should be... Okay, just a quick update. There's something weird going on here. As I bring the variac up to about 100 volts, I can hear this little sound coming from the board, a little click, like a little arcing sound or something. Don't know if you can hear it, I just heard it then. And there. So I don't like that. That could be quite hard to find. So I'm on 130 volts at the moment, and we've got 300 volts HT. That's clicking away quite nicely, that. Okay, I've put that ticking just to the side for the moment. I'm not sure what that is. There might be something arcing somewhere. But anyway, at the moment we're on half voltage, 130 volts going in, and our voltage across this 8K2 resistor is 49 volts. Call it 50. So power is given by V squared over R. So it's 50 volts times 50 volts, 2,500 divided by the resistor value, which is 8,200. And we're currently dissipating 0.3 of a watt in that resistor. Now, and that is at half of the input voltage. So that is all kind of in line, really. So let's just bring the voltage up a little bit more. That ticking is increasing, which makes me think it is some kind of arcing. I wonder if it's one of these electrolytics arcing inside. I can hear it. It's around here somewhere, I can hear. Anyway, look, we've got that's interesting. Did that... yes, look, okay, right, okay. We're on the trail of something here. I'm just going to turn this down a bit. Okay, now I think we might be on some sort of a track. Right, I've got it turned down now. We've just got 33 volts across here now. I don't know if you can hear that tick. I'm hoping you can. If not, I'll just kind of do that when the ticking noise comes. And you watch this voltage increase, i.e. the current increase dramatically through this resistor every time that tick happens. So I'm coming up now. 50, look. There, do you see that? See, it ticked and it clicked up to 180 or something. Wait for it again. There, it ticked and it went up to 200 milliamps. So there's a fault here. Could be in one of the valves. And when that fault happens, in other words, when that little short circuit or wherever it is happens, it pulls a huge load of screen current. And that's what's causing that. Okay, look, we've made some progress here. Right, one obvious thing to do is to pull the valves and to see if this still makes that ticking noise. That, of course, would eliminate a lot of things. So let's turn it up again. See if we can hear it. We're up to about 100 volts. Yes, oh, it's still doing it. Okay, that's interesting. Right, so it's not a valve. It's notoriously hard to locate sounds like that by sticking your ear in. It seems to be coming from everywhere, but if I had to guess, it seems to be coming from round about here somewhere. So it could be one of these electrolytic capacitors arcing across inside. Tricky. I want to pin it down really. Okay, you're going to love me. Having spent all that time telling you about the power dissipation in these various resistors, all useful stuff I'm sure, I've managed to get hold of a layout diagram for this exact amplifier, although I can't find a schematic for it, which is extremely weird, but anyway. And you know what, I'm not so certain now that this 8K2 resistor here is doing what I said I thought it might be doing. If you have a look, here is the line that goes to the 1K resistors. So they're using pin 6 here as a disconnected pin. It's not used, so just using that as a tag strip. So here's the screen voltage, goes in, going from this unused connection to pin 4, pin 4, pin 4, pin 4 on the valve bases. Okay, so here is the line that we're concerned about. It comes up here, it goes to this 8K2 resistor. Just ignore that for the moment. It comes across here, look, under the boards, and it goes to this, that's just actually 233 microfarads in series. It's giving 15 microfarads smoothing caps. And look, it's marked here choke, so this is one side of the choke, and here's the other side. So the HT comes in, goes through the choke, comes out the choke, and goes off for the screens. This 8K2 resistor is doing some more dropping of voltage, and that's going off to the preamp side. So that is very confusing, but that, you know, on that JTM100 diagram, you have an 8K2 resistor doing, you know, dropping the screen voltage. Okay, I've done a bit more investigation, and it's this side of the resistor that goes sharply down in voltage when you hear the clicking noise. This side of the resistor stays at 500 volts or so. So this drops down dramatically, and of course that would then put a big voltage across that resistor if this suddenly went down to 0 or something. So let's see where this goes. I think it goes to this capacitor here. This smoothing capacitor. So let's have a look. So it's this side of the resistor, and it does go indeed to this capacitor here. Yeah. So I think that this capacitor here is going short circuit. It's arcing across. So the sound is coming from this kind of area, the clicking, and imagine if this was arcing across inside and going short circuit. In other words, this you know, 500 volts here, 400 volts here or whatever, suddenly it goes to 0, goes to ground. You've got 400 volts across this resistor here, and that's going to get very, very hot if that starts doing that for any length of time. So my theory, my current theory, is that this capacitor is arcing across internally. Now I'm going to prove that simply by disconnecting it and putting another one in its place and see if that cures the clicking sound. So let's do that. Turn off. Let's see what we're doing in terms of voltages hanging around. It might have all discharged, but we need to check. I've got 51 volts on there, that's okay. I'll live if I touch 51 volts. But chance to use my trusty capacitor discharge tool, so I'll clip this to ground and we'll touch this on here, and it's got a 100 ohm resistor inside. Just discharge it like that. There we go. And I always double check, because who knows what can go on inside little boxes with switches on. So let's just double check again, and that's down to a couple of volts, 4 volts, so that we're good to go there. Right, let's whip this, it's the easiest way probably here. Just feeling, see if it was hot. Right, there we go. Right, that's that out of the way. Let's crock clip this in for the moment. So ground up that way. Positive is here. We'll clip the positive on there. And the negative on here. Like so. We'll put it somewhere safe where it can't do any harm. Just there, that's okay. Right, now we can turn on again and see if our clicking noise has gone away. Fingers crossed, eh? Okay, here we go. So we've got 100 volts. And it started clicking at about, well, varied really, 150. We're up to 150 now. Looking promising. 160, 170. Haven't heard a thing yet. 200 volts. AC going in. I'm just winding up the variac stage left there. 230 volts. There we go. We've got full voltage. Whilst we're here, let's check the DC on this thing. From memory, this is insanely high. I say, okay, so plate voltage. Look at that, 560 volts. Absolutely bonkers. These KT66s can only just take that kind of voltage. That's on the limit of what they're able to take. Screen is 560 volts. Oh, sorry, here's the screen here. 550 volts. That's right on the limit of what these KT66s are able to take. Okay, so that's looking quite promising, and I was on a complete wild goose chase there with that 8K2 resistor. But in case you think I'm mad, you know, excuse me, but haven't we got a 8K2 resistor here feeding the screen screen resistors? We certainly have. 8K2 resistor there feeding the screen resistors. That's not true at all. Basically, that resistor and my 8K2 resistor is this one here, which is marked 10K on this circuit diagram. So we've got an 8K2 there, and these screens resistors go straight up to the other side of the choke and the centre tap of the output transformer. In other words, they've got full HT on them. Red herring there. I'm leaving all this in. I'm not editing any of this out because I want you to know, I want you to enjoy following through the full proper fault finding process where you can find yourself right up the wrong path chasing something which you're absolutely convinced is right, and then suddenly thinking, hang on a minute, something really weird going on here. So we've actually fixed this. It's a arcing HT cap. Now of course I've got a huge question mark over these other caps here, so I need to speak to the client now to see what he wants to do in terms of me replacing them. First thing to do is to turn off. We've got a 600 volts hanging around loose here, which I'm not happy about. We'll just pull this and have a quick look to see if the HT is coming down. It's gone to pin 3. Yes, coming down dramatically. Look, it's only 50 volts already, so we're nice and safe. That cap's discharged, got 50 volts on, don't care about that, and we're safe. So we can disconnect this. I can just short the cap out just to get rid of that 50 volts, and we're good to go to replace this 33 microfarad at 450 volts. Righty-ho, I've had a word with the customer, and he wants to have all the caps done, which I think is exactly the right decision. So we're going to replace this one here with a 600 volt cap. There we go, and we're going to replace all of these with 33 microfarad at 450, all 7 of them. We're going to replace these with some 30 microfarads at 500 volt that we've got here. Yeah, I think they'll just about go in. And these are in series, so the capacitance is halved. but the voltage is double, so these are well within their ratings. Even these have got 900 volt rating, 900 volt and 900 volts, so these have a 1000 volt rating, 1000 volts, so that's fine. It's just a question of whether we can get them in nicely or not. I think we probably can. So I'm going to push ahead now and start changing these, which will take me a little while, so I think we may as well start with this one. I don't know how much of that you want to watch really. Oh, by the way, there's another one here which is 15 microfarads at 450 volts, so we'll do that one as well. These look okay, the other two are probably okay too. There's a couple of little small ones up here. Right, that's the plan. Okay, I might just show you one or two of these just so that you get the idea. First thing to notice is that all the positives are downwards, so we can't go wrong in terms of polarity. So we'll take this one out. Oh, I see, that's interesting. They're held in by little rubber bungees. Oh well. There we go, there's the first one. One rubber bungee. That doesn't want to come out. Now we could put a little dab of hot melt glue on there to hold those in. Okay, so we'll just put a little bit of hot melt glue on the bottom of here. Stick that down. It's very good stuff, hot melt glue. That's absolutely rock solid now. Always have the legend uppermost so that the next person in here can see what you've done. Oh, absolutely rock solid. That just came off there. Okay. Let's try again. It wasn't very hot, the glue, actually, so maybe I was a little bit premature there. There we go. Right, so it's a question really of getting a good mechanical connection here. There are lots of different ways of doing it. These tag boards have just a little tiny V in the top, and as soon as that's occupied by one wire, which yeah, this one is by the red wire, you've got nothing else left to solder on, so it's not a particularly clever system. But that will do nicely on there, look. And what have we got over here? Same sort of thing really. There you go. We'll solder that and then we'll make that look a bit nicer. Positive down, yep. You might not believe it, but I have actually soldered one of these in the wrong way before now. Didn't turn it on though. So I always triple check. That is perfect. That's reasonable, and we'll just take this little bit of off like that, and I'm happy with that. So now it's a question of moving on to the next one. It's just a kind of procedural thing really. I'm slightly concerned about being able to get these bigger caps in here. They're just a little bit bigger. take these bungees out. Yeah, weird system. I don't know what they're tied to under here. Anyway, get rid of those. I think I'll do these both together, these two caps. And having done these two, I won't bore you with the other 4 here. We'll just do these. That one's out. Let's get the bungee off first. I've never seen this system before. Right, let's see now how 2 of these are going to squeeze into there. I'm pretty sure we'll be able to do it, but so the sort of plan is we'll maybe put one here like this, and the other one kind of like that, so they end up just a little bit kind of offset like that. I think that's better than trying to cram them in there. That's okay, yep. So I think I'm going to start with the top one. It's a little bit more awkward. Yeah. So cut off the end. I'm just going to see if that's a sort of tag that you can push a connection down into. No, it isn't. It's just got that little funny little groove there that right, so I need to come down a bit with this and then across, something kind of like that. And then this one here. Right, I think I'll put a bit of hot melt glue on at this point. There we go. The glue gun's a lot better now, it's all melting quite nicely. Okay, so we can wrap this one around here. I won't solder that yet, I'll do it when I do the other capacitor. That's good. Yeah, happy with that. So we can solder that top one. Positive downwards, positive downwards. Okie doke, now we'll put this one in. And yes, I think we're going to go around here like this with this one. Not too easy this, these tags aren't great, don't like them very much. So something, oh, we've ended up, yeah, okay, we've ended up doing what I didn't want to do. But actually that seems to have worked okay, so let's chop that length off there. Put some hot melt glue on. Like so. Now this can go kind of like this. That's absolutely fine. Ouch. There we go, and that's two of them done, so I just need to repeat for these caps here. Similar kind of arrangement. There we go, happy with that. There's a little bit of lead floating around here. There we go. Positive, positive, positive. They're done. Join me when I've done these. Okay, I've done all those 7. Not terribly easy. This one was slightly rotated, but you can see perfectly well the legend from that side. All done. Positive, 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 positive. Yep. Those 2 are back on. These wires here are very low temperature sleeving. The slightest heat on there and the sleeving just peels back and melts. Terrible stuff. So I had a little bit of a job attaching those nicely. And okay, I think we're good really to power it up and just check that it all comes up in terms of voltages. We haven't heard a peep out of this amp yet, of course. So there are no valves in it for starters. Right, so we'll just plug it in. Little meter out. Turn it on. So I think we'll just check some voltages over here really. So that's, of course, we've only got 86 volts AC going in, and this is a couple of 100 volts DC already. Amazing. Right, we've got 150 volts AC going in. We've got 360 there on the screens, 370 there, 380, 380 on the HT, 380 on the HT. Bring it up a bit more. We're now 200 volts going in, 400 on the screens, 500 on here. 500 volts. I hate having 500 volts kicking around inside of an amplifier. We're not even on full voltage yet. There we go, 230. 480 on the screens. This will come down a bit, this HT, because there are no valves in it. So the valves will draw current and cause this to sag. So we're up to nearly 600 volts on, no, 500 volts on here, and that's a 600 volt cap, so that's okay. Remember, these are in series with each other, so the capacitance is halved and the voltage is doubled. By the way, this is not a terribly good way of doing this. You should have a 220k and a 220k series resistor in here in parallel to balance the voltages across here to make sure you get half of the voltage on the middle. I bet you this, well, let's have a look, see if it's half. That's 587 there, 286, 4, 5, see, it's not quite half. 282, see, it depends on the resistor, you know, on the sort of the value of the capacitor and the resistance, internal resistance of it, but you should have some balancing resistors there. Yeah, anyway, there you go. You know, this is a 500 volt cap, and it's got 280 volts across it, so absolutely fine. Same here, look, 280 volts. Oop, what I did there, must have accidentally touched the case of the cap. And our 600 volt cap has got 500 volts across it, 480, so we're good there. That's all good, I'm quite happy with that. What next? I'm going to change this capacitor now, and then we can get some valves in and finally see if we can get a noise out of the thing. That would be nice, wouldn't it? For the sake of completeness and just to help those who like a little bit of theory, I thought I'd just show you what was actually going on with that amp. So here's the HT line here. This is ground. This is HT, 550 volts or whatever it is, DC. It's got a smoothing capacitor, and there's probably a choke in here somewhere, but don't worry about that. Here is our 8K2 2-watt resistor that we were so concerned about. Not in the feed of the grid resistors as we thought, but actually acting as a resistance dropper to feed the preamp HT, which will be a lower voltage than this 550. And here's another smoothing capacitor here. These are 33 microfarads at 450 volts, 500 volts or whatever. These are our HT caps. This was the faulty capacitor. It was arcing inside, effectively short-circuiting, and every time it arced you could hear this sort of noise, ticking as it arced across. Every time it arced it effectively short-circuited. Well, just imagine that we did short-circuit this for the moment, not just for a few seconds. Then we've got 550 volts, an 8K2 resistor, ground, a huge power will go through that resistor and it will burn out. And the reason it didn't just burn out instantly was because, of course, this was not a short circuit. It was only short circuiting for, I don't know, a 20th of a second every second or something. But over time that's certainly enough to pulse a lot of power through here and take this resistor out. So that's what was going on. I thought you'd like to know. Here's the faulty component. This very old 33 microfarad at 450 volts. Right, so the next thing we can do now is put some valves into this beast and see if we can actually get any noise out of it. Okay, moment of truth. I haven't turned this on yet. You're seeing it as I'm seeing it. I've got two valves in temporarily, two bias meters. I've got it on the variac, and I'm just going to wind the variac up. It's all switched on, and we're currently at 75 volts AC input. These have come to life, though not showing very much at the moment. There we go, it's starting to register some plate volts here. 430 volts. And the current's coming up, which is good, and we're only at half power at the moment. Half voltage going in, I should say. We're up to 200 volts on the input before these valves sprang to life. But up they're coming, which is great. And look how the HT's dropped. Remember I said it was 550, which is way too high. But with the valves on, it's loading the power supply and bringing down this HT. So we're up to 10 milliamps or so on each valve. Of course, if I put another two valves in, it would load it even more, and this HT would come down even further. So let's go up to full voltage in. Okay, right, well, we're up to full voltage now, and in fact I'm just going to bypass the variac to put proper full voltage on. Let's come up even higher, look, nearly 600 volts on this. Yeah. Do you know what, I'm just going to turn that down, and I'm going to put the other two valves in. I don't like 600 volts on anything in this, really, particularly these valves. They're not designed to take 600 volts. Let's see if these two extra valves load the circuit sufficiently to bring this down to something sensible. But the bottom line is it's all working, which is good. We're getting some current, and I'm not seeing anything I hate in terms of current going through these valves. I'm winding it back up again now. This is now already at a sensible level, 490. We've still got a little way to go. That's 220 volts AC going in. And I'll bypass the variac now. So that's full. Well, there we are, 600 volts. Good grief. Bonkers. However, let me point out something else to you. That's 600 volts at 12 milliamps. Again, I'm just going to turn this down a bit. So these valves aren't pulling very much current at all. The more current they pull, the more they sag the HT. So I'm now going to find out what that current should be. We'll go for like 500 volts on the HT and see what the correct current for for this is. So I'll bring up my Weber bias calculator, www.tedweber, and we will enter in KT66, isn't it, for the valve? Yep. Right, tube type, I think it's got KT66 here, I hope so. Yes, it has, yep. Not a valve that I see very often, very, very rare for me to see this. I'm going to put 500 volts in there, calculate bias, and it should be 35 milliamps, just there. So we're at 12, so the bias on this is way off. So we now need to bias this amp. I have no idea how to do it, but I'm sure I can find out by flipping it upside down again and having a look at the bias circuit. So let's do that. Righty-ho, we are good to have a go at this. Here's the bias circuit here. One diode does some rectification and it gets smoothed by these two capacitors here, and a bit of kind of voltage drop via that 15k and this resistor here. I'm just going to kind of take a guess at what does what at the moment. So let me just tell you what I'm going to do. Let's bring the power up to full. Yeah, I'm just going to keep it lower for a moment. I don't like that 600 volts floating around. I've got a lovely little device here. It's called a resistance decade box. It allows me to dial in any kind of resistor I want. I'm just going to take a guess at the moment that the one I want to adjust is this one here. I could be wrong, but I'm just going to put a resistor in parallel here with this one, and let's have a look what it does. I've got 200k at the moment, which is very big, a big resistor dialed in. Let's just see what happened there. Okay, so that's correct. I'm on a low voltage going in at the moment. Let's put it on 200 volts AC going in. There we go. 500 plate volts, which is all I want. Don't want any more than that. We've only got 7 milliamps going through the valve. So watch what happens when I dab a 282k. That's just random. I don't know why that's set to that. A 280k resistor across this one here. Boom! Up goes the bias current, and down comes the plate voltage because more load is being applied. So we want about 37 milliamps here. So now I do feel comfortable about bypassing the variac and applying full power, and at full voltage going in. Currently with this 280k resistor we've got 570 plate volts and 30 milliamps bias current through the two outside valves. And I'd like a little bit more bias current, so I'm going to reduce the value of this resistor here. 270, 260, see the bias currents coming up, look. 250, 240, 230, 220 would be a useful value, and that's looking nice, isn't it? 220k. Yeah, we'll go with that. And the plate voltage has thankfully come down a bit to a whopping 560, 570 volts DC. Completely mad. That is out of the spec of these valves here. It's how it's been designed. There's nothing wrong with what we're doing here. I went on some forums and they say that this is how this beast is supposed to work. So it's pushing these KT66s right to their limit. Bit bonkers in my view, but there you go. So what I'm going to do now is to solder a fixed 220k resistor across there, and then just recheck that the bias is 37-38 milliamps. Now we haven't actually heard anything out of this amp yet, so why don't we just plug something in. I haven't heard a peep out of it yet. I haven't even plugged a guitar into it. Okay, it's buzzing. It's making a lot of buzzing. Why? Right, let's plug a guitar in, see if it actually even works. Hope I'm not going to get involved in a long song and dance about trying to find a buzzing noise on this amp. Right, that's in. Yeah, that's working. It's also very loud. Right, I'm not going to worry unduly at the moment about that buzzing noise. Let's get the bias sorted out. It's a bit of a funny amp this. It's a mixer amp basically, it's a PA amp. So it's got 4 completely separate inputs in and 4 volume controls. And it may be that we've got one of the volume controls. Don't know, not worried about that at the moment. Let's get the bias sorted. So what was I doing? Yes, I'm going to put a fixed resistor in here. One thing at a time basically. Let's get that sorted. Alrighty, well when I remeasured that combination there, it came to 40k, so not sure what I did the first time. I must have misread the meter or something, thinking it was 47k. Anyway, I didn't have a 39k 2-watt resistor, so I've gone for what I was originally going to do and have that extra resistor in parallel. Bit of an overkill in terms of wattage, that resistor, but that's fine. So let's turn it on and see now if the bias is going to behave itself. That's 200 volts AC going in. HT's already up. Just waiting for the valve to warm up now. You'll start to see the current increasing here and the HT will start to decrease. Remember, we're not on full yet, so we'll go full voltage in. Up comes the bias current. That's looking a lot better. Look, we've got 37 milliamps on one, 38 on one and 35 on the other. 3 milliamps difference, perfectly okay. Bit of a hum on this amp, I'm not quite sure what's going on there. Sort of mainsy sort of hum. Hope we don't have to spend hours tracking that one down as well. It's there with everything down at 0. Oh, off on that one. Yeah, a bit hummy that. Anyway, that's not the next job. The next job is to turn off. I'm happy with the bias. Remember, 38 milliamps roughly. The next thing to do is to swap the bias meters from the outside pair to the inside pair and just check that the bias is still around about that kind of level. So to do that, we're going to turn the amp up back the other way again. Okay, I've just taken the bias meters off here and put them on those valves. That's all I've done. And I just want to check that, first of all, those 2 valves are working, and secondly that the bias current is kind of similar to the other 2. Right, we're all plugged in and we'll turn on. There we go. This is showing weird readings because there's not enough voltage going in to power the actual circuitry inside. So I'm just winding up now, 170 volts. There's the HT look. Looking for current to start coming on these valves now any minute. There we go, they're starting to warm up, starting to draw current. We're up to 210 volts, we may as well just bypass the variac and go full voltage. There's that hum again. And the good news is, it's looking good, look. 37, 38 milliamps and 36, 37. Fine, nicely matched quad of tubes these. Very nice. Good. Right, so what shall we do next? It's all biased up, which is brilliant. And we solved the main problem, which is good. I think I'd like to see what's going on under here. What have we got in terms of preamp tubes here? Don't know the history of this amp. Oh, there's the 4 fairly new looking JJs in there, so they should be okay. They're not, I'm not looking at 1965 tubes or anything there. About 1965-66 this amp was made. Righty ho, so right, there we are, swung it round. Yes, that's quite a kind of nasty hum, that. Right, let's turn all these volumes down. See, it's got 4 volume controls here, 1 for each of the PA inputs. So I'm guessing this is a sort of early band amp, really. You plug a singer's microphone in there, a guitar in there, another singer in there or something, you know. You've got a kind of a mixer amplifier, mixer PA amp. So we go into number 1, and it's got 1, 2, 3, 4. They're actually labelled loudness 1, loudness 2, loudness 3 and loudness 4. Turn up that, and I can immediately hear that we've got a signal. That's great. Quite loud too, that's good. We may as well just check all these inputs whilst we're here. That's good. Number 2, turn up the volume. Yeah, that's good. 3. That's good. And 4. Right, so I'm happy with all that. Let's check whilst we're here. Let's just check the other controls. Any input will do. We're going to input 1. It's a very basic amp. This has just got 4 volume controls, bass, middle and treble, and presence. That's it. That's all you've got. Treble. Yeah. That's okay. Middle. It's there. Can't hear that much. Bass. Yeah, bass is working. Presence. Yeah. Not much difference between that and the treble control really, but anyway, there you go. So in my view, this amp is good to go with the exception of this hum. So here are these 4 inputs. Look, identical, kind of high and low level inputs. This would be called, I think, a high level input because it's got some padding in it which reduces the level. It's always a bit confusing, that, I think. And this would be the low level input, which has got more amplification. And then look, you've got 4 volume controls, 1, 2, 3, 4, 1 for each input. So it's just a mixer amplifier, that whole front section. Then you've got a simple bass, treble and middle, and then a presence control and an indicator lamp, and that's all you get with this. I've been reading up on these. I think this is the one that Jimi Hendrix used or something, so they're quite sought after these days. People like them. Okay, well, I'm not sure how much time to spend chasing this hum, but anyway, you can hear it quite clearly there. Let me show you a little diagnostics trick. We really want to know, is the hum coming from the preamp side, one of the inputs maybe or something, or is it something on the power side? One thing you can do there is just pull the phase splitter valve. That's this valve here. Just literally pull it out. Oh, that's interesting. Funny enough, I didn't quite expect that. I thought this might be on the power side just because it wasn't affected by any controls. So pulling the phase splitter has killed the hum, which tells us that the hum is in the preamp side. We can carry on with that little exercise. I'll just turn it off for the moment. And we can go along using the same trick to push the problem. It could be noise, by the way, it could be hum, it could be a crackle. To isolate it, start pulling valves in sequence this way and see if you can push the problem down into earlier stages. Right, let's turn it on again, and we'll do the same trick with this valve here. Completely killed it. Alright, so the hum is at quite an early stage here. Let's try this one. Still there. So it's here or here.
pulling this one won't do it. If pulling that one didn't do it, pulling this one certainly won't. If you see what I mean. There we go. Okay, so the hum is past here and up to here. So the hum is here somewhere, you know, in the area of this V3 valve. One thing we can do immediately is to replace V3, but only because it's easy. I don't expect for a minute that to do anything, because it's quite rare to have a valve that hums like that. Makes a very nasty hum. Let me just go and grab a new ECC83. So just to remind you, pulling that valve had no effect, so it's not that valve. Pulling that valve had no effect, so it's not that valve. Pulling this valve, and the hum went away immediately, so it's either associated with this valve here or something in between this valve and this valve. There we go. And just to eliminate the valve, I'll pop in another one. I don't expect that to have any effect whatsoever. And there it is. Just as bad as predicted, but it was worth doing because it just takes seconds, so why not? Next thing then, let's flip this upside down and have a little look around here, see if we can find out what might be going on, what might be causing all that hum there. So we are looking in the region of here. Look, this is the valve that we pulled out. Pulling out that or that had no effect whatsoever. Pulling out that and pulling out that killed it, but so did pulling out that. So it's not that valve, it's here somewhere. Now, I don't even know whether the amp has always been like that. It's always a problem. If someone brings me an amp and says it's been fine but it's just suddenly started humming, then I can start looking. But if someone brings me a 60-year-old amp which they bought off eBay or whatever, you know, how has it been humming for 60 years? I just don't know. Okay, that's on full now. You can probably hear the hum in the background. First thing I want to do is start moving some leads around. Listening to see if any of that hum goes away. Or decreases in volume. Got a screened lead here, look, which is taking the signal from here to here and then on to here. It's a strange arrangement, that. I presume that's original. Sometimes the smallest movement on these leads can cause dramatic differences in hum. These are the heaters here, these twisted pairs, so of course they've got 6.3 volts AC all over them. This is called lead dressing, if you're interested. Sometimes adjusting the dressing of the lead can make a big difference to hum, but not in this case. Okay, we changed this capacitor here, and that's the smoothing capacitor for a lot of this stuff downstream here. We didn't change that cap, but that's just a cathode bias cap. I don't think that will be causing any problems, so is that one. Well, good morning, another day, another dollar. This is my third day on this amplifier, and I'm chasing this hum problem this morning. Hum is a difficult thing to chase. You can spend a lot of time on it. It's almost always caused by two things. Either the power supply is hummy, in other words there's some AC ripple on the power supply, or there's some kind of hum loop, pickup, induction in the wiring somewhere. The latter is of course much more difficult than the former.
This is the capacitor that does the smoothing for the preamp side, and this morning I've dabbed 100 microfarads across there. Currently it's 22 microfarads for 50 volts. I've just tacked 100 microfarad across there, didn't make any difference whatsoever, so this is not caused by any kind of power supply hum. We know it's around this V3 area here, and we don't know whether this has always been like this or whether it's something that's happened. So I'm a bit concerned about maybe having to spend a long time on this. Hum problems can be very intractable. Also, take a look at this. There's no screening here. Look at all these unscreened wires coming from the pots. So the jacks come in unscreened and they go to the various valves. My guess is that V1A does channel A, V1B channel B, V2A channel 3, V2B channel 4. Remember, there's no schematic for this. All unscreened, and then here are their associated pots, 1, 2, 3, 4. Again, just ordinary equipment, hookup wire here, no screening, but moving this around doesn't seem to have any effect, so I don't know really what's going on here. Anyway, let me show you, we'll make a start on it and let me show you how we go about solving this. So on this valve here, which is the faulty area, this is the unused pin. In other words, that's where the gap in the pins would be, and this is pin 1. So pin 1 is the anode of V1A, and pin 2 is the grid, control grid. So this is where the signal comes into this valve, this is where it comes out. Now here's a trick you can do. You'll probably throw your hands up in horror, but you can actually short circuit. I'm just going to clip onto ground here. I can actually short circuit pin 1. It goes via this 100k up to HT, HT being the HT for the preamp side, so about 350 volts. So you're effectively putting 350 volts across a 100k resistor for a short time. I wouldn't leave this on too long, but of course what you're doing is grounding the output, killing the output of V1, and you can tell whether the problem is there or not. So I'm just going to do that quickly, and that killed it completely. No hum whatsoever. So we know that the hum is coming in V1A somewhere. Now this is the input to it. This, I don't like this arrangement here. Hard to believe this is original, but yeah, maybe it is, I don't know. And I think what this valve is doing, again in the absence of a schematic, is mixing effectively the 4 outputs. And look, it comes to this point here and to this point here, and each of these has got 470k, 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 470k. So I think these are the inputs from the wipers of the pots, and they're getting mixed down. Remember, that's short circuited to that, mixed down into one signal and being fed to the pin 2, the control grid of this valve. So this is just mixing the 4 inputs together. So let's have a go at seeing what happens if we now short circuit the input to the valve here. And that's gone down a little bit. Now let's do it over here. Again, it's gone down a little bit. A better way to do it is to go right on the ground here, where the screen is picking up its ground, or I could have just clipped onto here and short circuit it then and see what happens. Oh whoa, that's interesting. So that, look, has completely killed the hum. Now what's interesting is that this, in theory, is ground as well. So clipping onto here should have killed it too. And it doesn't, it reduces it by a little bit. Now that sort of implies, let's just turn this off a second. This is feeling like some kind of ground loop, high impedance ground problem to me, which is, they are so hard to sort out. So this should be ground. This is the negative side of the capacitor.
let's just see. Short circuit gives me 0.2 ohms on this meter, so let's go from there to this ground. It is ground, but it's interesting, isn't it? You know, so it's 0.3 ohms, so basically this ground is not identical to that ground, and that's how you get hum loops in equipment. That's exactly what happens. You get a slight impedance between the different grounds that you supposedly have. In other words, you bond something here to what you think is ground, you bond something over here to what you think is ground, you bond something here to what you think is ground. All the pots get grounded. I'm doing my inverted commas thing, and they are all ostensibly ground. If you measure it with the meter, you know, you haven't got 100 ohms or anything, but you might have 1 ohm or 2 ohms, and that's just enough to set up a ground loop. Right, now where were we? Okay, now what I'm going to do is that. So let's turn it on again. What I will now do, we know that killing the input to the mixer kills the hum. So the hum is coming down the line here from the earlier stages, but we know that if we pull V2 it doesn't kill the hum. I'll just double check that. I haven't done that for a while. There you go, that's V2 out, look. And I bet I can pull V1 as well. Ta-da! So that hum, there's no valves in there now, so this is a ground loopy sort of hum being picked up by this kind of mixer circuit. Now I believe, my guess is that these ends of these resistors will go to the wipers of these pots. Let's just confirm that. It would be so much easier if we had a schematic on this. It's very strange that there's an excellent layout for this online. I mean, literally, look, perfectly created layout, but no schematic. Obviously one could sit down and create it from this, but no one has. Anyway, we probably don't need it, so let's just see if this goes to V4, the pot 4. It does, look, so that's a short circuit from the wiper of this pot to this one. That's channel 1 of the mixer, if you like. This will be channel 2 of the mixer. It is. This will be channel 3 of the mixer. It is. And this will be channel 4 of the mixer. If I get on there, which I can. So it's just as expected. The amplified signals from V1AB, V2AB come into these pots here to the top of the pot, and as you and then as you turn them up, they get applied to the wipers of the pot, which then gets mixed down into this mixer. Right. So what we should be able to do is to now start short-circuiting the wipers of these pots. Now, in theory, they should be short-circuited, of course, because don't forget when we've turned our controls fully anti-clockwise, the wiper is connected to here, and as you can see, look, these have been grounded. This is ground. That's bonded to the pot, bonded to the pot, bonded to the pot, bonded to the pot, and takes its. There's a ground here. I don't know where that actually goes to get its ground, but that is grounded. However, let's just do something here. Right, there's our nice hum. And let's see what happens when we short circuit. I'm going to go onto the ground here for the moment. Actually, no, let's go over to the ground here. We know that now short circuiting this kills it. Like that. How about if we start short circuiting the wipers of these pots, which, by the way, should be shorted to ground anyway, because I've got them all fully turned down. So here we go. That went down a little bit. That went down by the same little bit. That went down by the same little bit. And that went down by a fair bit. Now I bet you if I short circuit all of these wipers, no guarantees here, but let's see what happens. This has already gone down 50% nearly, the hum. So let's now do the same for this one. That's gone down another 50%. Wonder if I can just do it on the chassis. Yes, I can. This one. And this one. There we go. Completely killed it. So that is now cured. Now of course these should be at ground already, so let's now transfer these clips to what is supposed to be ground. It's this wire here, tinned copper wire, that's bonded to the back of the pots and goes all the way along and picks up its ground from God knows where. I'm guessing it will have the same effect. Interestingly, it hasn't. That's interesting. No, that has not had the same effect. Aha. How peculiar. Well, this is doing my head in a bit, I don't mind telling you. It's not making sense. Okay, so I've got this clip to the ground nearest to this valve, and we know that if we touch it on the wiper, particularly this one, I don't know if you can hear, the hum goes down dramatically. That's less than 50%. And if we short circuit all of these wipers, it goes down to 0. So we can just concentrate on this one. Hopefully you can hear the difference between that. Now this is short circuited to there because the pot's in its anti-clockwise position, and this is ground, in inverted commas. So you would think that touching this on here would have the same effect. So watch. 50% less hum. No change. This is short circuited. I'm going to keep putting that in inverted commas because we might be talking about, you know, half an ohm or something, which can be significant. But look, that is, oh, that's 12 ohms. That's interesting. That's interesting. So that isn't actually short circuited there. It's just gone down to a very low ohm. However, all right, but follow me through on this one. So you think, well, let's really make this a short circuit, and the hum will definitely go away, of course. No. So putting that on there kills the hum. Putting it on some, let's call it some random tag next door to it, and then short circuiting this to this has no effect at all. I'm completely mystified about that. I don't understand that at all. This is now short circuited definitely to there because I'm touching it with a crop clip. Doesn't even change it slightly, whereas that knocks it back 50%. Huh. Okay, I've been about another hour since I last spoke to you, and just to show you how intractable these kind of hum loop problems are, I made a little bit of progress. I've got some very heavy duty cable here, and watch what happens when I short circuit this ground spot to the back of the pots, or to the back of the pots. So listen. Goes down 50%. Watch what happens when I short circuit it to this ground here, which is the pots taken to here. Ooh, it's gone down to manageable levels. So this is just a hum loop issue, and due to a very small impedance between this point here and that point there. Let's turn off the amp and see if we can measure it, and I bet you it's under 1/10 of an ohm or something. This isn't a super accurate meter, so short circuiting the probes together, that gives me 0.2 of an ohm. So let's see what we've got between our point here and here and here. It is 0.2 of an ohm. But I bet you that's 1/10 of an ohm difference there. I just don't have an accurate enough meter to read it. Interesting, isn't it? You know, effectively we've got short circuits all around on the ground, but there's just enough impedance there to create this hum. Right, now I want to see what happens when I take it back to this central spot here. That's the central ground for the amp. That should be roughly short-circuited to here. It is. So let's turn it on again. It looks like we may be able to get ourselves out of trouble here by taking a real hard solid ground from here straight back to here, even if I have to use thick cable like this. So we're going to go, obviously be careful dabbing around here with voltages and things, and you don't want to be grabbing all the end of this and dabbing around in here, but let's go from here to here, and it kills it by say 75%. Is there any difference between there and there? Yes, that's more hum there than there is here. Yeah, there's quite a significant difference between that and that. That's about 50% of that. So just this little link here, this wire here is inducing the hum. Let's try back to here. No difference. Okay, well, I'm not going to ponder the whys and wherefores. I'm simply going to make myself a nice solid piece of wire from here back to here, and hopefully that will solve it. Okay, I've got the amplifier off and unplugged, and I've discharged the caps. I'm going to use this wire here. This is just stripped out of some electrical domestic twin and earth wiring, quite thick copper, and the plan is to run it from here. I'll probably run it up along here and across here and down to there. I'm going to make a new earth tag there, clean that off, put a brand new earth tag on, and bond this down onto here. Obviously we're going to be insulating this as well. That's the plan. That'll probably take me, I don't know, maybe 20 minutes, half an hour. So when I've done that, I'll show you what I've done, and more importantly, we'll see if it actually works. I think what I might do is leave it off. I'll probably route it all around and just leave it disconnected here for the moment, so that we can just tap it on and see if it actually does the trick. Okay, so I'll put a new solder tag in there and put this big piece of wire on, and it runs along here, up here and along here eventually when I dress it. At the moment it's just hanging loose here, so now I'm going to be able to dab it onto here. So I'll shut up so that you can get a feel for the hum. I'm hoping you can hear it. And there's the difference between that and that. So quite a significant difference there, bringing it down to manageable levels. You wouldn't believe it, but I can hear another problem on this amp now. I can hear a kind of a fried eggy sort of noise, you know, the usual sort of noise. Quite low level. I might try changing a couple of valves here, see if that goes away. But anyway, for the moment I'm going to run this along neatly and put it on there permanently. Well, just to keep you amused, I've just spent 5 minutes working out why the amp isn't working. I thought I'll give it a go now. I've turned it on, the hum is, you know, it's there, but it's a lot less than it was. And I thought, well, it's not working. I've got the guitar plugged in, I've got the volumes up. What's wrong with it now? And of course, I happen to notice these two on the bench.
3 and 4. Goody, so that's all working, and the hum is, I think, acceptable. Great, we are slowly getting there with this. I'm just going to swap that V. Oh, that's interesting. Yeah, okay, so I had a kind of gash ECC83 in the V3 position, so that's just when I pulled out the junk box just to see if it was the valve. So that might be where that noise is coming from. Anyway, let's put the proper JJ back in. With a bit of luck, that crackling sound I heard will have disappeared. Great. I can't hear that noise now. So it was that tatty old valve I put in temporarily. Whoa, I think, you know what, I think we're done. Oh, well, phew. That was a bit of a struggle, that amp. It took many hours to get it sorted, but I'm quite pleased with how it went in the end. I could easily have edited out all the mistakes I made and made it look much more super slick. But I'm getting the impression from people who watch this channel that they really like to follow the fault finding procedure in kind of real time. In other words, warts and all, errors and all, stupid mistakes on my part and all. And my idea is really to leave all those in because that's where the learning is. I got badly sidetracked by that 8K2 2-watt resistor, but I think you'll agree it was a reasonable sidetrack since I had the schematic from the JTM100. It had an 8K2 2-watt resistor in the feed to the screen resistors, but I didn't have the schematic for this, which I must admit really didn't help. It would have been very useful to have the schematic for this. Bit of a sidetrack there, but we got back on track eventually, and found that ticking arcing capacitor, and then of course we chased the hum problem, and that was quite a good one. It's reasonably common, I don't know, 1 in 50 amps or something have some kind of hum issue, and this one was a more difficult one because it wasn't a simple smoothing capacitor, it was some kind of ground loop issue. I don't know if you know, but audio amplifiers, I mean by that I mean hi-fi amplifiers, always have a star earth system. Every single earth gets taken back by a separate cable to a central earthing point, usually a solder tag on the chassis. You don't earth the pots up one end of the chassis and the negative electrolytic capacitor down the other end of the chassis and something else on the far right hand corner of the chassis, believing the chassis to be earth. Of course it is earth, but you can have a very small resistance between these various points, and that can cause something called earth loops, and you can end up with a hum, and that's exactly what this amp had. And I don't know about you, but it looked like this amp had it from new to me. I mean, there was no fault with the amp, it was just the way they'd earthed those various inputs. So, no idea. Anyway, it's fixed now, and the customer is going to be very happy. It's a quite rare, quite collectible amp, and I know he's looking forward to using it. Well, that's it again from me. Thank you very much as always for watching, and I hope you enjoyed the content. I'll catch you on the next video.